Imagine trying to run like a massive global shipping warehouse.
Okay.
We are talking petabytes of inventory here.
Got it.
And every single time a shelf breaks or a new shipment arrives or the layout just needs to change, you have to send this literal army of workers sprinting through the aisles.
Oh, that sounds like a nightmare.
Right. They're manually moving heavy boxes, updating paper spreadsheets, and, just hoping nobody trips over each other or drops a really fragile package.
Yeah, I mean, it sounds incredibly stressful
Yeah.
and practically begging for human error, especially when you factor in the sheer speed at which things actually need to move today.
Exactly. And for a long time, managing massive amounts of data felt exactly like that chaotic warehouse.
Very true.
So today we are taking a deep dive into some really fascinating source material. We've got architectural documents and production-grade YAML configurations for a technology called Rook for Ceph.
Which is such a game changer.
It really is. It basically turns that chaos into a self-driving machine. Our mission today is to demystify how infrastructure engineers are solving one of the most notoriously difficult tasks in all of tech.
Deploying and operating distributed storage at scale.
You got it. If you've ever wondered how modern applications handle petabytes of data without collapsing, or requiring an army of engineers to manually replace failed hard drives, this is the secret.
To really understand the solution, we first have to look at the tension it's resolving. The documents we were looking at focus heavily on Ceph.
Right.
And for years, Ceph has been the absolute gold standard for open-source, software-defined storage, mainly because it unifies block, file, and object storage into one massively scalable system.
Historically, though, getting Ceph up and running and actually keeping it happy was brutal.
Oh, absolutely.
You were dealing with this messy cocktail of Ansible scripts, manual system units, passing around SSH keys, and tweaking these intricate configuration files.
It was a very hands-on process.
Very. And if you are an infrastructure engineer listening to this, you know that manual approach clashes entirely with the dynamic, declarative world of Kubernetes.
Because Kubernetes expects to just declare a desired state, right? Like, I want this much storage with this much redundancy, and have the system just figure out the rest.
Right, but traditional Ceph required constant babysitting.
Exactly. And that massive gap is what Rook was built to bridge. It's a CNCF-graduated Kubernetes operator.
So before we get into the deeply technical YAML configurations, I think we need to clarify what Rook actually is.
Good idea.
Because it is not a storage engine. It doesn't physically store a single byte of your data.
No, it doesn't.
The source documents refer to it as an automated supervisor, or a localized site reliability engineer, and SRE for Ceph.
Right.
Okay, let's unpack this, because I look at a claim like that and wonder, is calling a piece of software an SRE just marketing spin for a fancy deployment script?
Well, what's fascinating here is that a traditional deployment script, or even something like a standard Helm chart, just follows a static recipe.
Right, it just executes steps.
Exactly. It applies a set of configurations once. If a server physically catches fire 10 minutes later, that script doesn't know what to do. The system just breaks.
Yeah, script doesn't react to the kitchen catching fire.
Precisely. But Rook operates through a continuous reconciliation loop. It's a classic Kubernetes operator pattern of observe, analyze, act, and update.
Oh.
It actually acts like a human SRE because it dynamically reacts to changing conditions in real time. Like if you alter port properties or increase a replica count, it makes those decisions on the fly.
Okay, let's break that loop down mechanically. First, the observe phase.
Sure.
Rook is constantly monitoring the Kubernetes API server for any changes to the desired state you declared.
Right. And simultaneously, it is watching the physical reality of the cluster. So the status of the worker nodes, the physical disks attached to them, the health of the running pods.
Okay, then comes the analyze phase.
Yeah, it compares the actual physical reality it just observed with the ideal state you declared in your YAML files.
And if there is a delta between the two, it moves to the act phase.
Exactly. And this is where things get genuinely complex.
Right. Let's say a worker node hosting a critical Ceph monitor pod suddenly fails. The motherboard literally just dies.
A standard script would just fail there.
Right. So what does Rook do in the act phase?
Well, Rook detects the node failure, and it automatically spins up a new monitor pod on a healthy node.
But spinning up a pod isn't enough, is it? Ceph is highly stateful.
Right, you can't just spin it up and hope for the best. Rook then automatically joins that new pod to the Paxos quorum.
Wait, let's pause on Paxos, because that's a term that gets thrown around a lot in distributed systems.
It does.
A Paxos quorum is essentially a strict mathematical voting system, right?
That's a great way to put it.
It ensures all the monitor pods agree on the exact state of the storage cluster, so you don't end up with like a split brain scenario.
Right, where two halves of the cluster think they are in charge and start corrupting data.
Yeah.
That is the exact mechanism. Paxos requires a strict majority to agree before any cluster changes are committed.
Oh, wow.
Yeah, by automatically adding the newly spun up monitor pod to that voting quorum, Rook ensures the storage cluster survives hardware failures.
Without a human engineer ever having to wake up at 3 a.m. and manually edit the cluster map.
Exactly. And finally, in the update phase, Rook sends telemetry back to the Kubernetes API, logging the recovery so the rest of the system knows the current status.
Okay, I admit that dynamic decision-making justifies the SRE title.
Right.
But an alive, perfectly balanced storage cluster is entirely useless if your application pods can't physically get to their data.
Very true.
So how does Rook bridge that specific gap between, an application requesting storage and the Ceph backend providing it?
This brings us to the Container Storage Interface, or CSI, and the terminology here trips up a lot of developers.
Oh, absolutely.
We have CSI drivers and CSI plugins, and they perform entirely different functions. Think of the whole process like a global delivery service.
Okay, going back to the warehouse analogy. I like it.
Yeah, so the CSI driver is just the language. It's the shipping standard.
Right.
It translates a high-level customer request from Kubernetes, like deliver a 10-gigabyte box of goods, into structured instructions that the storage backend can actually understand.
And according to the architecture docs, Rook deploys two distinct types of these drivers. Essentially speaking, two different storage dialects.
Exactly.
First, you have the RBD, or Rados Block Device Driver. That gives you high-performance block storage, utilizing a read-write once, or RWO access mode.
Right, and you'd use this for something like a PostgreSQL or MySQL database that needs incredibly fast, raw block storage dedicated to a single node.
Because the database needs exclusive locking over those blocks to guarantee transactional integrity.
Precisely. And then you have the Ceph-FS, or Ceph File System Driver.
Okay.
This dialect is optimized for shared file access, supporting read-write-many or RWX.
Got it. So this is what you deploy when multiple different pods spread across your entire cluster all need to read and write to the exact same directory simultaneously.
Right, like a distributed content management system serving images.
Okay, so the drivers dictate the language and the rules of the road. But a shipping standard doesn't actually drive the delivery truck.
No, it doesn't. That heavy lifting is left to the CSI plugins. They are the workers executing the protocol, and Rook splits them into two groups.
Right. First is the provisioner plugin. This acts as the back office coordinator, right? It sits up in the Kubernetes control plane.
Yeah, the coordinator's job is purely administrative. A persistent volume claim, a PVC, comes in from an application.
Oh.
The coordinator contacts the Ceph warehouse, reserves the requested 10 gigabytes of space, and writes down the reservation ID.
But the back office provisioner never leaves the control plane.
Exactly. It never touches the actual physical data or drives the truck.
Which leaves the actual physical connection to the node plugin.
Yeah.
This is the on-site delivery driver. Rook deploys this plugin as a daemon set, meaning it is stationed on every single worker node in your cluster.
Right. And when the application pod spins up and is ready for its data, this local node plugin jumps into action.
Let me make sure I have the sequence right here.
Yeah.
It uses the Linux kernel's RBD module to mount the physical storage container, right?
Yep.
Which then shows up on the host operating system as something like dvrb0.
You have the sequence perfectly, and once the node plugin exposes that block device via the kernel, it formats it with a standard file system lock.
Like XD4XS.
Exactly. Then it takes that formatted volume and physically bind mounts it directly into the application pod's isolated namespace.
Here's where it gets really interesting. It completely shifts the bottleneck.
How so?
Well, you go from days of procurement, manual LUN mapping, and zoning fiber channel switches, to a developer simply making an API call that resolves in milliseconds.
Oh, right.
Thanks to Rook deploying these plugins, if you're a developer, you never have to worry about kernel modules or device mapping. The storage just magically appears inside the container.
What stands out to you about this level of abstraction?
Just how completely invisible all that complexity becomes.
Yeah, the speed of that abstraction is phenomenal, but it also introduces a massive physical risk.
A risk.
Yeah, we are talking about this delivery network acting logically, taking orders via a Kubernetes API. And Kubernetes is notoriously abstract.
Right. It just sees raw compute resources.
But hard drives are fiercely physical. I mean, they are chunks of metal and magnets physically plugged into motherboards.
That's true.
How does a cloud-native abstract system actually know what physical metal is plugged into the servers?
Ah, okay. Well, Rook bridges the abstract and the physical using a specific daemon set called Rook Discover.
Right.
When enabled, the operator deploys a privileged pod to every single node. And this pod periodically scans the host server's physical hardware bus. It utilizes native Linux command line tools like udev and lsblkey to scan for raw, unformatted block devices.
So it essentially acts as a scout.
Yeah.
It builds an inventory of the raw materials available across the entire data center that can be converted into Ceph object storage daemons or OSDs.
Wait, if we have a robotic SRE aggressively scanning the hardware bus for drives to consume, my immediate fear is accidental destruction.
Oh, for sure.
How do we stop this operator from scanning the bus, finding the main operating system drive, running Kubernetes, formatting it, and completely wiping out the server?
That's a valid fear. But Rook implements strict safety mechanisms directly within the Rook Discover daemon to prevent that exact scenario.
Okay, good. How does it do that?
The daemon explicitly ignores any device that contains an active file system.
Oh, that makes sense.
Yeah, it ignores drives with partition tables, and it ignores anything with an OS mount point. It is strictly looking for completely blank raw disk real estate.
Okay, phew. So it takes those findings, like the disk path, the capacity, the serial numbers, and writes them to a specific config map in Kubernetes.
Exactly.
But looking at the production YAML configurations provided in our sources, infrastructure engineers don't just rely on that automated filter, do they?
No, they don't. In the Ceph cluster configuration file, engineers use strict manual hardware targeting.
That is the device filter property.
Yes. Instead of telling Rook to just consume every blank drive it finds, an engineer will provide a regular expression.
Okay, for example, NVM119. Let's unpack that regex for a second.
Sure.
The Kira symbol means it must start with NVM, and the bracketed numbers mean it has to be followed by a digit from 1 to 9, so NVM1, NVM2, and so on.
Right. By doing that, the engineer is enforcing strict intent.
Right.
They're telling the operator, even if you find a blank SATA drive or an unformatted USB thumb drive plugged into the server, ignore it.
Right. I only want you to provision OSDs on these very specific dedicated NVMe drives.
Exactly. It prevents the automation from making bad assumptions about your hardware topology.
Speaking of topology, Ceph's entire architectural claim to fame is high availability, right?
Absolutely.
Data must be replicated across different physical locations, so a power outage in one rack doesn't wipe out your entire company.
Yep.
Traditionally, engineers had to manually map out their data centers, calculating which racks and rows held which servers, and feed that into a CRUH map.
Right. CRUH is the controlled replication under scalable hashing algorithm.
Okay, that's a mouthful.
It is. But think about it this way. A traditional storage system uses a central lookup table to find data. Like, where is file A? Let me check the index. Oh, it's on drive 4.
Right.
The problem is, at petabyte scale, that central index becomes a massive bottleneck. Every single read and write has to check the table. CRUH completely eliminates the lookup table.
Oh, wow. So it uses algorithmic math instead.
Exactly.
When a client wants to write or read data, it runs the CRUH hashing algorithm locally. And the math dictates exactly which physical drive the data should live on based on the current cluster map.
Yep. The client then talks directly to that specific drive.
But for CRUH to distribute data safely, it needs to know the physical layout of the hardware.
Right.
So rather than a human manually doing the math to map host racks and data centers, Rook automates the CRUH map by using Kubernetes as its source of truth.
Exactly. It reads the native Kubernetes topology labels, things like topology.kubernetes.iozone or custom labels like rack E1.
So Rook reads those labels and dynamically constructs a matching CRUH hierarchy in Ceph.
You got it.
When you declare in your YAML that you want your data to survive a physical zone failure, Rook ensures that the data replicas are mathematically distributed across different physical zones.
Right. So if a backhoe cuts the power to zone A, the CRUH algorithm guarantees that a full accessible copy of your data is sitting safely in zone B.
And clients instantly know how to calculate its new location.
Exactly. That bridges the physical and the abstract perfectly for storage drives. But, another crucial component of the physical layer is the network.
Oh, right.
Now that we have physical drives mapped, safety checks in place, and storage flowing automatically, what happens when the system hits a massive production load?
That is where network traffic jams become catastrophic.
Oh, entirely.
Because Ceph is an incredibly chatty protocol. You have client applications constantly reading and writing their data.
Right.
But behind the scenes, Ceph is also constantly talking to itself. It is replicating data blocks, rebalancing the cluster after a drive failure, and constantly checking health heartbeats.
And in Ceph architecture, those two streams are separated logically. You have the public network, handling client reads and writes, and the cluster network, which handles internal data replication and recovery.
Okay.
If both of those heavy traffic streams share the exact same physical network interface card on your server, a sudden burst of internal recovery traffic can completely starve your client applications.
Okay. It's like realizing your highway is jammed because local delivery vans and cross-country freight trucks are sharing the exact same lane.
I like that.
Yeah, if there's an accident that causes the freight trucks to slow down, the delivery vans are stuck in the traffic jam too.
Yeah.
Database queries start timing out, not because the database is slow, but because the storage network is too busy fixing itself to actually answer the query.
Exactly. To solve this, the source architectures utilize Multis CNI, a container network interface plugin.
Oh.
Normally, a pod in Kubernetes receives exactly one IP address on the primary cluster network. Multis breaks that rule.
Oh, really?
Yeah, it allows pods to have multiple network interfaces simultaneously.
And it pairs Multis with a technology called McValnia.
Right.
I understand the mechanics correctly. McValnia basically takes one physical network interface card on the server and splits it into multiple virtual interfaces, each with its own unique MSC address.
You've got it perfectly.
So it bypasses the standard Linux bridge entirely, allowing packets to route directly to the pod with almost zero overhead.
That is the core mechanism. By defining network attachment definitions in YAML using McValn, Rook can bind the public traffic your delivery vans to one physical VLAN, let's say interface Eth1.
Okay.
Simultaneously, it binds the heavy cluster replication traffic, the freight trucks, to a completely different physical interface, like Eth2.
Wow. Multis basically lets Rook pave a completely separate, dedicated highway just for the heavy freight trucks.
Exactly.
It guarantees wire-level isolation. So no matter how hard the storage cluster is working to rebuild itself after a massive hardware failure, it physically cannot consume the bandwidth that your applications rely on.
Right, the network isolation secures the bandwidth, but the architecture documents also detail how to secure the actual data access.
Which brings up a critical custom resource definition called the Ceph client CRD.
Yes, which enforces least privilege access.
Because most internal applications just use the CSI drivers we discussed to get standard storage volumes. But in a real-world enterprise, you often have external systems, like a massive corporate backup system or a custom S3 object gateway that need to bypass Kubernetes completely and talk directly to the raw Ceph storage backend.
And handing a massive backup system full admin access to your entire storage cluster is a massive security risk.
Oh, absolutely. So the Ceph client CRD allows infrastructure engineers to generate cryptographically secure Ceph keyrings natively using declarative manifests.
Right. You define exactly what permissions the external system requires.
Okay.
For example, you might restrict a monitoring tool to read-only access across the board. But for that backup system, you might declare allow RX pool backup pool.
So you are isolating its read, write, and execute capabilities entirely to one specific pool.
Exactly.
And when you apply that YAML, Rook connects to Ceph, generates that heavily restricted cryptographic key, and automatically writes it into a native Kubernetes secret.
Yep. The external workload just mounts that secret and authenticates safely. The operator entirely manages the lifecycle and security posture of those keys.
Wow. By unpacking the mechanisms behind the YAML, the transformation becomes so clear.
It really does.
What does this all mean? We started by looking at a chaotic warehouse relying on human engineers, spreadsheets, and handcarts to manage petabytes of data.
Right.
What Rook does is fundamentally rewrite the operational model. Rather than forcing administrators to manage storage through archaic command line scripts and SSH tunnels, Rook elevates Ceph into a fully declarative self-healing component.
Completely.
By mastering things like multi-network segregation, strict regex hardware discovery filters, and automated CRUSH topologies, you can build petabyte-scale storage fabrics that run seamlessly under Kubernetes.
You really turn what is arguably the hardest part of infrastructure into an automated utility.
Absolutely.
But, if we connect this to the bigger picture, it raises a philosophical question about the future of our field.
Okay, I'm listening.
We are looking at a landscape where software operators dynamically discover physical drives, partition them, route isolated network packets, and heal complex distributed quorum failures without human intervention.
Right.
If software operators like Rook can completely replace human SREs for something as dangerously complex and physical as distributed storage, what is the future role of the infrastructure engineer?
That is a fascinating question.
As we build systems that automatically discover, format, and manage the very metal our data lives on, are we abstracting ourselves out of understanding how the physical world actually supports the cloud?
Man, when the robotic warehouse manages itself so perfectly, we might just forget how the shells are even bolted together.
Exactly.
Something to really think about. Well, thank you for joining us on this deep dive. Keep questioning the layers beneath your applications and keep exploring the unseen systems that keep your technology running.